In the last video, we talked about using binomial PDF to find the probability of exactly X successes in N trials. But sometimes we don't necessarily want to know the probability of exactly X successes. We want to know the probability of at most X successes or at least X successes. How do we do that? Well, the cumulative um, binomial CDF is the cumulative probability function on the calculator, and the C stands for cumulative. That means it adds up several probabilities for us. On the TI-8384, the command binomial CDF and then the same arguments N, P, and X on the calculator provides the sum of all probabilities from x equals 0 through the specific value entered for x. So it's going to, if I type in the probability of, let's say, binomial CDF 10, comma, 0.3, comma, 7, then the calculator is going to add up the probabilities from 0 through 7. X is where I tell the calculator to stop adding. In other words, to find the probability of at most X successes in N trials, if each success has a probability of P, go to second and VAERS, that's the distribution menu again, scroll down to B, which has binomial CDF, and then press enter. After you enter the values of N, comma, P, comma, and X, and then enter again. For example, if the probability of an individual having group O blood type is 0.45, find the probability that at most 2 out of 5 randomly selected donors would have group O blood. Now, if I just selected 5 people and said how many of these 5 people have group O blood, then the answers would be either none of them do, or all of them do, or somewhere in between. I want the probability of at most 2. At most 2 means 2 or less. And out of 5, at most 2 would indicate either 0 or 1 or 2. I want to add up the probabilities of 0 or 1 or 2, and that's when I use binomial CDF. N is the number of trials, P is the probability of having group O blood, because that's what we called a success, and I want the probability of at most 2. So 2 is where I want the calculator to stop adding up the probabilities. Binomial CDF 5, comma, 0.45, comma, 2 gives me a probability of about 0.593. So in other words, if I selected 5 donors, there's about a 60% chance that no more than 2 of them would have group O blood. Now you have to read very carefully to know how to find each probability based on whether it says find the probability of exactly X successes or at most X successes, or perhaps we'll even run into at least X successes, and we'll talk about that in just a minute. But when I want the probability of exactly X successes, that's when I use binomial PDF and enter the arguments N and P and X in that order. Binomial CDF gives me the probability that there are at most X successes. That adds up all the probabilities from 0 to whatever X value I enter at the end of that argument. For example, if P is 0.2 and N is 8, circle the numbers which are implied by at most 5. At most 5 means the same thing as 5 or fewer. And so at most 5 out of 8 refers to 0 through 5. What would you enter on the calculator to find the probability of at most 5 successes? We don't want exactly 5 successes, so we're not going to use binomial PDF. We're going to use binomial CDF and enter the number of trials, 8, the probability of success on one trial, 0.2, and the x value is the last value whose probability I want the calculator to add in. I want it to stop adding at 5. So binomial CDF, eight, comma, 0.2, comma, 5 is about 0.999. That's the probability of 5 or fewer successes out of 8. Now there's one other scenario. We've talked about exactly X successes or at most X successes. What about at least X successes? At least X means X or more, X or X plus 1 or X plus 2, or so on. For example, circle the numbers which are implied by at least 6. At least 6 includes 6 and everything bigger than 6. Now, this is not the probability that the calculator will give me. Binomial CDF always starts at 0 and adds until I tell it to stop. It won't start with 6 and add to where I tell it to stop. So somehow I have to figure out how to get the probability of at least 6 using what the calculator will give me. Well, notice that if at least 6 means 6, 7, or 8, the complement of that is 0 through 5, and that is what the calculator will find for me. I can find the probability of 0 through 5 by using binomial CDF, out of 8 trials, each trial having a probability of 0.2. What's the probability of at most 5? And that will give me this probability, which is the complement of the probability I want. If I have this probability and I want that probability, just subtract the probability I have from 1, and you can enter that straight left to right on your calculator. Make sure you're choosing binomial CDF. What's the probability that out of 8 trials, each having a probability of success of 0.2, what's the probability of at most 5? That's, well, actually, that's the 0.999 that we came up with just a minute ago. So the probability of at least 6 is 1 minus that, or 0.001. When you want the probability of at least something, you're going to have to find the probability of its complement and then subtract that probability from 1. All right, let's do a few more examples. If success is defined as having Group O blood, and the probability of success is 0.45 on a single trial, find the probability that at least 3 of 5 donors have Group O blood. If I randomly choose 5 people, then the answer to the question, how many of them have group O blood, would be either 0, 1, or 2, or 3, or 4, or 5. If I want the probability of at least 3 means 3, 4, or 5. But that's not what binomial CDF will give me. Binomial CDF is going to add from 0 up to wherever I tell it to stop. That's the complement of what I want. So all I have to do is find this probability with binomial CDF out of 5 trials, each having a probability of success being 0.45. What's the probability of at most 2? And once I have that probability, I can subtract it from 1 to get the probability that I'm looking for, the probability of at least 3. And by the way, you can enter that straight left to right on the calculator. You can say 1 minus before you pull up binomial CDF. And then go ahead and enter the size of the trial is 5. Probability of success is 0.5. And I want the calculator to stop adding at 2. So 2 is the last number I enter. And that probability rounds up to 0.407. The probability of getting at least 3 out of 5 donors with group O blood, there's about a 40% chance of that happening, maybe 41%. If I have to have 3 pints of group O blood, is it very likely that I'm going to get all 3 pints from just choosing 5 donors? Well, there's about a 40% chance that I will, but there's about a 60% chance that I won't. I would say no. There's about a 60% chance that less than 3 will be obtained. No, actually, it's 59%, but I'm just trying to answer this question as simply as I can. All right, one more problem involving finding probability. A medical testing laboratory saves money by combining blood samples for test so that only one test is conducted for several people. If combined sample test positive, if at least, let me try that again. The combined sample test positive if at least one person is infected. If the combined sample tests positive, then you have to go back and do individual tests. But medical laboratories save a lot of money with batch testing for diseases that are fairly rare. This one just happens to be about gonorrhea, and the probability of a randomly selected person having gonorrhea is 0.00114. That probability is so low that rather than doing blood test on every single sample, the CDC will combine 30 samples and test that combined sample. If everybody in the sample is clean, nobody has gonorrhea, then the lab has saved a lot of money by only having to conduct one test rather than 30. However, if the batch test comes back positive, then the CDC has to go back and do individual tests on the groups of 30. Find the probability that no one in the sample is infected. Well, does no one mean at least something, or at most something, or exactly something? Find the probability that no one is infected. Sounds like the probability of exactly 0. And if I want to find the probability for exactly 0, I would use binomial PDF since it says exactly. And I would say out of 30 people, each having the probability of 0.00114 of having this disease, what's the probability that exactly 0 of them do? I got that to be about 0.966. That means about 97% of the time, the whole batch comes back testing negative, which means no one in that group has gonorrhea, and the labs just saved a lot of money by conducting only one test instead of 30 tests. We also need to find the probability that the combined test positive with at least one of the 30 people infected. Well, there's an easy way to do this and a less easy way to do it. We could say at least is 1 minus binomial CDF and add up from 0 to 29. Or we could just say at least 1 is the complement of none. Either none have gonorrhea or at least 1 does. So we already have this probability of at least 1 is 1 minus the probability of 0. And we said the probability that no one, that the whole batch is negative is 0.966. So the probability that at least one person in the batch of 30 is infected is only 0.035. In other words, about 97% of the time, the batch test will be negative. About 3.5% of the time, the batch test will be positive, and we'll have to go back and do individual tests. The final question is it likely that such combined samples test positive? Well, that 0.034 is less than our cutoff for what we consider usual. So I would say it's unlikely or unusual that the batch test would be negative. Excuse me, I'm sorry, unusual that the batch test would be positive.